So we're going to continue our discussion about probability today. I'm going to start with a simple question, and we'll go from there. So let's say you're choosing one card from a deck of 52 cards. And I could ask for probability. So for example, I could say, what's the probability that the card we got was a 3 or a 5? Well, you know something about the deck of cards. You know that there are 4 threes, 4 cards with a 3. There's a 4 of hearts, diamonds, spades, and clubs. And then there's 4 fives, the same suits. So we can say there's a 4 to 52 chance of getting the 3, and then another 4 to 52 chance of getting the 5. So we add those together. This is 8 out of 52. Okay. Let's ask a question and see what you think about this one now. So suppose I say, what's the probability of getting a 3 or a red card? Now, you got to be a little bit more careful here. Let me show you what someone might do that would not be correct. They might say, all right, well, there are 4 threes, and then half the deck is red, so then 26 out of 52. And you got to be careful, because we know that 2 of these red cards, 2 of these threes are already red. So if we just added these fractions the way we were, or the way they are, we'd actually be double counting the 2 red threes, because the 2 red threes are in this fraction, or being counted there, and they're also being counted here. So what we want to do is subtract off the overlap, subtract off the cards that are being double counted just once. Okay, and then if we do that, we get the correct answer, which is 28 out of 52. Okay. So it turns out this question here, this is a pretty important question. So let's try and visualize it and then come up with a formula, and then we'll be set. We're talking about something called a Venn diagram. And what a Venn diagram is a way of visually representing sets. So in this particular case, let's consider set A, and we're going to say A is going to be the set of all the cards that have a 3 on them. It's all the 3s. And then there's another set over here, B, and B is going to be the set that contains all the red cards. And you'll notice I've drawn these circles so they overlap, and I've done that on purpose because there are some cards that are in both sets. So for example, the cards in here that I've shaded in the red, these are the cards that are red and have the number 3 on them. And you actually know what those cards are. It's the 3 of hearts, and it's the 3 of diamonds. Okay. So then, you could think about this question carefully. You realize what's left in this side. Well, on that side are the 2 threes that are not red. That's what those are. So those are 3s that are not red. And then over on this side, these are the red cards, or the reds I'll say, that are not 3s. Okay? And when I ask for the probability of a 3 or a red, just so we're clear about this word or means something very specific in mathematics and in probability. It means that you can be a 3, or you could be a red, or you could be both. So it's not an exclusive or. Sometimes you hear the word exclusive or, and that means you could be 3 or red, but not both. So this or means that we can have a 3 or red or both. So what is that telling us? It's telling us that what we're really looking for is the probability of being in this whole region. Now if you think about this from an area perspective, what we want to do is we would like to add everything that's in the A circle plus everything that's in the B circle. I should be careful there. Or I should say the A circle and the B circle. But if I just did it there like that, if I left the formula this way, the problem I would have is I'd be counting this area in the middle twice. So I need to subtract off the probability of being in circle A and in circle B. Okay? So generally, what we say is the probability of A or B equals this expression. Okay. So let's go back now and use this formula. It seems like we needed this in the case where we had the 3 are reds, because there were cards that were 3 and red. What if we tried to use it on the first problem where we said 3 or 5s? Well, the probability of getting a 3 or a 5, if we drew a Venn diagram for that, and here's what you could do. You could start and draw the picture this way and say, all right, here's the 3s, here's the 5s, and the part you have to realize is this picture is a little misleading. You can see that there's overlap here, but the truth of the matter is there's no way a card could have a 3 and a 5 in it. So this thing here in the middle is empty. So if you're going to do a better job drawing this Venn diagram, what you would do is you draw a Venn diagram like this, and you'd show 2 circles. Here's the 3s, here's the 5s, and there's no overlap. That would be a better way to show it. If we use the formula that we had, the probability of a 3 or a 5 is equal to the probability of 3 plus the probability of 5 minus the probability of a 3 and a 5. And what you notice is the probability of a 3 is 4 to 52, plus the probability of 5 is 4 to 52, and the probability of being 3 and 5 is 0, because there's no way you can be both. Just so you know, when we say that the probability of A and B is equal to 0, we have a term for that. That means the events A and B are mutually exclusive. So that's one way to say it. Instead of writing mutually exclusive, you can also use the word disjoint. Okay, so disjoint is a synonym for mutually exclusive. This just sort of confirms that you can utilize this probability of A or B formula equals probability of A plus probability of B minus probability of A and B in any situation where you're talking about or. All right, let's look a little bit more, just a couple more comments about notation and Venn diagrams, and then we're set. So we can ask you to shade in certain sections of a Venn diagram. So for example, suppose I said, what is the set A this? Now that symbol in the middle I haven't discussed yet, but this symbol means intersection or intersect. You should think of it like the word and. Okay? So when I write this notation, what I'm really saying to you is, where is the region where we're in A and in B, or A intersect B? So here's circle A, here's circle B. The intersection of those is right here. Okay, a couple more comments about Venn diagrams. Sometimes you'll see notation like this, A with a little c above it. That's read A complement. And what that means, everything that's not in A. So here's circle A, maybe I still have circle B around here. But if we're not going to be in A, that means we have to be outside circle A at all times. So all of this region that I'm shading in blue is outside in circle A. What you'll notice is it does contain some part of B over here, but that's okay because we're just interested in not being in A. That's what A complement means. And then you can start asking interesting questions, like for example, you could say, what's A complement intersect B? Well, we just drew a picture of what A complement looks like. And now what I'm saying is I want to be outside of A. That's what A complement means. And I want to be in the circle B. So on the picture, here's what that looks like. Here's set A. Here's set B. And as long as I'm in here, I'm outside of A, but I'm inside of B. That's what that means. Okay, you could also do even fancier looking things. So for example, I could say, what's A complement intersect B complement? It's the same thing as saying, I want to be outside this region I just drew in the previous problems. I don't want to be in there. Well, that's actually pretty easy to do. Since we know what it looks like to be an A complement intersect B, here's A, here's B, we just don't want to be in that shape. So we'll shade everything outside of that. And there you go. Okay, so now I'm in the complement of A intersect B. Now one more fun question to think about. What if I asked you to do A with a U B complement. U means union. But you should think of that as the word or. So this question is saying, how could I be in A or B complement? That's what that's really saying. So let's start to think about what that picture has to look like. So here's a Venn diagram. Here's A. Here's B. And sometimes the easiest way to do this is just check each region. So let's talk about this. Let's say I'm outside here. Well, if I'm outside in here anywhere, then I'm outside of B, which means I'm in B complement, and that's good. Because for an OR statement to be true, just one of these has to be true. So this could be true, and this could be false, or this can be true, and that could be false, or they both can be true. So if I'm outside here, all of that would have to qualify, because that makes this part true. Now, I also have the option of being an A. So if I look at this, or I look at the picture, here's some A right here. So this region here is all A. Now this particular part of it, if we just look at this side for a minute, that's I'm in A and I'm in B complement. So that's this case. But I haven't considered this case yet. I've already done the last case. So this case, I can be in A. Well, that would mean we'd add on this little piece of extra area, because that's okay to be in. So here you go. The only thing left is this, which you'll notice if you look at these two pictures I've just drawn, they look exactly the same. We've left the same area unshaded. And that's because when you take an expression like A complement intersect B complement, you can sort of, for lack of a better word, you can sort of like distribute this onto all three pieces. It's actually called De Morgan's law. And then A complement complement, the first piece really becomes just A. And then the intersection becomes a union. And then B becomes B complement. Well, if you think about it, that's exactly what we just did.